So, hi, some new faces here. I'm Reen, and I will give you, no, it's like I will start some of the lectures, but Koit will be back tomorrow, Wednesday. And what kind of lectures I'm giving, so you have had quite like theoretical knowledge so far. So I will try to benefit more like from the practical side. I have routine laboratory experience, about 10 years, and I worked also in accredited laboratories with an LCMS. So I have a little bit different background. My main background has been an environmental field, so water, different sediments, and also like biota samples, fish, and things like that. So I have done a lot of method development over the years with different analytes, and really LCMS I've seen in my dreams and nightmares and good dreams, so I know all about it. So today, because you already have a little bit of knowledge about how chromatographic separation takes place, and you've heard about the reversed phase chromatography, about helic chromatography. So now today I will just introduce a little bit how do they look like, or what the columns are, and also maybe just give a little bit of context. Some of the things are in a detail that we are not going all the way like how a specific stationary phase works, because you know how a reversed phase chromatography works. So we are not going to look, oh, so this column has this group and we'll like analyze it further. So that's not the idea. The idea is to give you an understanding what the options are and what kind of analytes you might like use, what kind of columns, and we will have some practical things coming on the weeks also. Then next week I will start with instrumentation, like practical problems and what even to know about LC and MS instrumentation. Then we'll talk about detectors. So what kind of detectors in addition to MS? MS is just one detector, you can use others. And we will do a seminar on the detectors. So you have, I think it's already up, or I will make it available. There's like an Excel table where you can make, you can do first at home that, I think it's not, yeah, I will make it. Yeah, yeah. So you can have it and then we will do it together. So it's not mandatory to send it in before or anything. It's not like, but it's better if you do it before at home and then we will fill it in here all together. And these are, they are, so the only thing is that next 2 Mondays, it's also in the plan, the lecture will be only online. So don't come here, or I won't be here. So Mondays, next week and then week after. Wednesdays are all good and we'll do the seminar here and but the Mondays. I will write it in the forum also, but just some other things happening, so I can't be here. But I will do it live so that we can still have a discussion if you have questions, and so it should be okay. I guess we will just go into it and start going from it. Like I said, you know the theory, you know why we talk about what, you know what the terms reversed phase chromatography, helic chromatography, normal phase chromatography, ion chromatography, you know the basics. But for some reason, but we need somehow now to carry out this, whatever this is, this chromatography. And for that, we need some kind of a column that is, I was going to show you the columns, like physical columns. Okay, yeah, no, I forgot to take one. But basically you just need a tube that has this packing now when you are pushing through your eluent that it starts to do the chromatographic separation. And there aren't that many options actually to do this packing material, and we'll get into it why. And the main material is silica gel material, so basically small small balls basically, or like small particles. These are used, maybe you have seen like some kind of sample preparation, like preparative columns or something, but basically a tube with small particles. And even though it's something that's very important, because from the theory, you know that this particle size matters when we talk about separation and efficiency. And it has been changing, obviously, because we want faster, we want nicer peaks, we want better separation. So there's like this constant development in that field. And at the moment, we have reached like this little bit below 2 micrometer particles, so 1.8. And of course, at one point there comes a limit. They can't be like so small that it doesn't really work anymore, because you still have to push through the liquid through that. They have to be stable. So there are certain limitations. So not sure if we can actually go lower, not very likely. Then it probably needs already like changes into instrumentation, and we can't use what we have. And I would say past, I don't know, 20 years, I have seen the change from like this 3.5 to 2, and now more and more laboratories, because we have better, we'll talk about the instrumentation, but because we have better chromatographic pumps that tolerate higher pressures, we can have smaller particles. So this is kind of where we are. And so what these particles are, so we can like, these small little tiny balls, there are 3 types. The most common one is basically, there's a very nice picture here that it's just like a homogeneous, like this porous microsphere basically. And this is silica, and then you can use, so it has different, so when we talk about different diameters, so it has different, depending on the size and the pore size and the area. And so this is most commonly what you would see in a column. The second one that is becoming more and more popular are these microbelligerant particles that have like this solid core. So when these ones were like fully porous, so all the way like a tiny round sponge basically, then this has a solid core, and then only on the outer surface we have this area that's like effectively doing this chromatographic separation. And the reason is that then, your analytes, they can't like, they will only have the interaction like on the surface, and they can't like penetrate all the way in. So it means it's like shorter, like it's more efficient. You can get the separation faster, and it doesn't like, in a way that the analytes don't get lost here, like somewhere in the particle, which can make your peak wider. So they are more efficient. But probably the problem is a little bit that they also limit that the amount of analyte, you can't overload it, because it can also hold less. So if there's too much of an analyte, or you have too concentrated injections, for example, then there's not enough room for the analytes to basically separate, so they cannot get like. So this is something you have to think about if you have peak concentration, that the peaks actually can get broader in that sense. And I would say that today, or like past few years, they are getting like more popular compared to maybe 10 years ago. When they came, I actually remember when they came, because we got like the first column like for free to test it out. They are more expensive. They are, you can imagine, they are more complex to produce, because first you have to have this sphere, and then you have to like somehow make it such a way that it's covered, that it's uniformly covered. So there are more steps like from the production point of view. And also there might be problems with reproducibility. Are all the columns exactly the same when you order a next one, like from batch to batch? And so this is, it takes time to have this, that these columns are in such a way, like with any new technology, when it comes out, you know what, we don't know how it's going. And that's what I remember for the first ones. They clogged very fast, and the peaks, you know, they had very nice peaks, but like at very limited range where they worked nicely. But now you see more and more producers. But I think the first producer who came out with them was just a Phenomenex, and like nobody else made them. But now others are also making. So it means that there's something to it. So you might see this when you're online, you will see this solid core, or somehow they might have a different nice name to it, but that's what they are. And just because they are a type, are also these perfusion particles. But these you can see from the pore sizes already, like not very practical when we talk about like small molecule analysis, like small analyte analysis, you know, like pesticides or pharmaceuticals. Well, pharmaceuticals, of course, if they are like very big, some like biologic molecules, but overall, and the idea here is that these you even see that these pictures look like they are very old, and that's also that there aren't very many publications about that, and they aren't like commercially available. There are a few options there, but they are more really like if you are doing some kind of biotechnology and you really want to separate macromolecules and for that. So and the difference is that you see here that how these particles look like, that you are separating. It's not really about the chemistry itself, but how analytes are going through these particles. So that's a bit different, and it's because of how just liquid is moving. So it's less about like chemistry in that sense. It's more like physical physics, how these particles move through them, and they are either for macromolecules or when like for preparative chromatography when you are doing peptides. So nothing that we will go into any depth anymore, but just in case you see something like that, you know that it is out there, and it's just it's a little bit different how these molecules look, and you see that just, and depending then on what is the journey through these particles, then bigger ones move slower and smaller ones move faster, and that's how they separate. So let's go into silica, because this is the most common one. It still is the most common one as a base material for chromatography and for these columns. Yep. Yeah, it's more similar to that, but not only, but yes. Yes. So that's more there because it enters in one, and obviously it depends on how far it can go on the size and what kind of network of pores it has. So yes. So silica, just make sure that I can have the have this with me. So yeah, so when these some years, very long years ago, we also like talked a little bit how the silica material is actually prepared for the columns, but I have left it out because I think it's not very practical to know, but basically these particles are made of sand. It's just like a long procedure how they're made. They're milled, different heating solvents, like a lot of steps. And I'm not sure now, but there aren't very many producers even actually who make these like base silica gel particles, because it is very like precision job. You have to do it like very precisely, because you have to have these particles the same size and all this process and the chemistry and how they are. So there aren't that many. And I'm not sure, but I just remember when I was being taught, when you and Koit were teaching me this course, then I remember that they said that maybe like even 1 or 2 producers who made these particles, and they basically, all the column makers buy from them and then start to modify like according to what they want in their columns. But what happens is that because of this process and how they're made, how they look like is this, in the end, these particles, like before they go into modification phase, just like this silica particle, you can have basically like a bare silica particle that's nothing is done to it. It's just like a very, very tiny, like sand particle, basically. Of course, it has been modified in a way that it has a certain, like a diameter and also pore sizes. And also what you want is that these pore sizes are somewhat uniform. You can't have that it has big and like small. Otherwise, how can you buy a column with a particle size like 3 or pore size 100? So how you want it to be the same, and when you buy the next column, that it also provides you exactly same retention times, same peak shapes. So here is a nice like image how it really looks like. And what is good about silica is that you can actually make it in such a way that you can like categorize it and separate into these very like strict ranges, and it's spherical. So of course we want particles that are spherical if we are like packing them in the column, and they are rigid, so they are mechanically strong, and they have to be if we are pressing through liquid. So they can't just like break down with too high pressure. Of course, there are always limitations when you buy a column. There always is like a maximum limit. You can't have too much, but sometimes it's not really due that they would break down, but it's also that you can like pack it. If the pressure is too high, you will just push these particles like together too much, and then they don't work as they're supposed to. But I guess I have to actually, I don't know what would be the pressure where it breaks, but overall they should be. Let me see what is the difference between perfusion and porous particles. Porous particles they have like different pore sizes, but so it's like in and out. But perfusion have like all through the particle. So yes, sorry about that. Let's go back. But it is not like ideal. They still have problems. And one of them is that the pH. So the good thing is that like in water and our regular solvents that we would use in liquid chromatography, they don't swell. But the pH is what matters. Is it can break down, just because if the pH is too high, it will just dissolve basically in there. So it gives you some limitations if you would like to do. Probably Koit has told you what kind of, or maybe not yet, but like for the gradient dilution, or like what kind of pH your puffer should be, and like related to pKa and all of that. So, or if he hasn't yet, he will. Then you would think, eluent like pH 10 would be good, or 11 would be good. Then actually silica gel-based columns don't work. They will just dissolve. And the other thing is, if the pH is too low, it will go into these layers, but that will also cause the hydrolysis of this layer that is on top of this silica gel. So again, if it's so again, you can't go too low, but I think in most cases we are more in, like, from practical point of view, when we talk about different analytes that can be analyzed with LCMS, usually we come into the problem at the higher pH level. We would really actually like to have eluents that have a high pH, but then we can't. So we have to figure out, and we have some alternatives. We'll get to that also. And another thing is that because the surface is acidic, you see here, so it's an acidic surface. So it means that it starts to have like secondary interactions with your basic analytes that you don't really want if you have modified the surface. And I'll show you the picture. So there are certain like disadvantages, but there are ways to get around it, and you can modify it, and we'll get to that. But overall, when a silica particle is produced, these are the different types of like groups that can be on the surface of these particles. So you see, it's just these lone like acidic groups. We can have like metal ions in here. These metal activated. The metal is usually inside because of how they are made. So it's not that they're like intrinsically there, but during the manufacturing process, metals can get into these particles, so they can actually cause problems. And then we have these geminal groups, and then these vicinal. So you see that they have interactions with either like with each other or with like water. So with water molecules. So they start to have like, so it's not all like uniformly exactly the same. So this is basically the starting point. And so you know that for Helic, you can basically use just the bare silica particle. You can do normal phase chromatography and Helic chromatography without adding any. Have you heard already about C18 probably, that for the reversed phase? So, but this particle is just like bare particle, and you can actually use it for, but not for reversed phase, but Helic and normal phase. But you see, because there is a lot. So from the practical point of view, if you would just use this particle, what are the issues? Or if we replace, or if we add some kind of modificators here, then, you know, we might change, but we can't change like all of them. We'll still have some of them left. And so these lone acidic ones, why these are not good? Because they will start to interfere with these basic compounds. So they will you see here is they start, because they have like the secondary interaction, they will cause this peak, like tailing basically, because it's not like this fast, like efficient like separation or interaction that we want in chromatography, that, you know, it's stuck there and comes out like we change the element composition, and then you basically you lose the interaction, so you can separate them easily. But with this secondary interaction, it's like holds it a little bit stronger than like we would want this separation to be. So with pH, of course, if you see here, if the pH is changed, then like it's okay. But if the pH causes this, that these groups here are charged, they will basically just have an interaction with these basic components and cause this tailing. So if they are not, so if they're just like, if they don't have a negative charge, so then they are good, then they are not the problem. But at certain pHs, they will be a problem for your analysis. So you have to be aware, and that can happen. So this is what these groups are causing. Yeah.
I suppose that these pH of this cellular group, like, do you know the pK of these?
No.
When we can work with?
No, I'm not sure. I don't know by heart. Yeah, don't know. Yeah, sorry. Then we have these geminal groups, and because they are less acidic, so these are they aren't like a problem really. They can be there, but they are not causing any like direct effect that we would have to worry about. So if there are some left after modification of the surface, and also these the same with this kind of hydrated groups. So they can get hydrated. So then also they, we don't want too many of them, but they don't really interfere too much. So we'll see how these groups are really targeted or can be targeted during synthesis or like when they're making these columns. But these groups, so like the thing is that if you are synthesizing the columns or making the columns, that when there is a variation of these groups, like how much of an effect would they have, like from batch to batch? So are like different columns the same or not? So so this definitely has an effect, as like these groups are less of an interest there. And then, yes, I told you about the metals. So what they can do is also, because, metals can also like basically have an interaction with your analytes. In the same way, basically, they will just bond with analytes so strong that you can't, it just doesn't come out of the column, or again, you will have like broad peak shapes. Or the other way is that if it's like close to this lone group, it can also make this one more acidic. And then again, it will have an effect on your basic compound. So again, something that you would really like to get rid of, or that there are as few of these metals in the like material of the column packing materials. So this is like comes to like from the production point of view, or how these pair particles are, and depending now on how we are preparing this particle for our column, like if there are some of these left, how they would have an influence on your analysis. So that's the idea. And usually when we talk about this particle diameter, then of course not all the particles are not all exactly the same size. There's like a certain like range where all of them are. And of course, the more similar they are, the better repeatability it is. But so usually it's like plus to minus like 50% of some kind of like medium value that you have. And of course, then sphericals, and then you have pores inside them. So this is kind of like what we started also, that this is what we want this packing material to be. And now we are going into, like I said, with just this silica, we can't do reverse phase chromatography. We now have to do something with it, that we can have these interactions in the column. And that's where it happens that, in a way, these OH groups, these cylinder groups are good, because we can now modify them. We can have different like chemical reactions between these groups, and then we can add basically whatever we like to this particle, and then we can use this modified surface as our, we can use that for the chromatographic separation. So basically we can have like some kind of ligands and like the C18, and we'll get to that. So basically, this is the most simplest one. We can have like this monomeric surface that we add, like this C18, C8. We have to all of these silanols. We add like some kind of so with this we have very like non-polar than the surface that we can really now start to use for the reverse chromatography. For normal phase chromatography, it's a different story, but for reversed phase, so we need something. And mostly it's C18. C8, I think, was like more like old times, but now most columns, when we talk about like this most traditional reversed phase column, it's the C18 column. It can have some different additions and small modifications, but like on the base level, it's like the C18. And why? Because it's easy to make it in such a way that you basically just make the synthesis that you replace all these basically add to this OH group, you add this silica, and you can have this chain, and it's monomeric. It's easy to produce. There's not too much that can go wrong. You just basically attach it, and or maybe some are left behind and not reacted. Then we can worry about it, because it can cause then problem for the basic analytes. But like overall, it's quite effective. And that's why also these columns are popular, because they are quite simple to make and then have a lot of different applications. However, it is also possible to have like play around more and not have just the C18, but have like this kind of like a polymeric surface. What do you think is a problem with polymeric surface, as opposed to like this, or this like nice monomer? What is usually, what do you know about, I don't know if you have had like a course on polymer chemistry, but what is the problem? Yeah, that we will talk about too, but what is like from the polymeric reaction point of view? Yeah, you can't really control, like, where do these reactions start to happen? It just starts to polymerize it, but like what reactions, like how many places, like where are they interlinked? You can guide the polymeric reaction like with certain conditions, of course, like the temperature, the concentrations, maybe like the ratios of different chemicals. But overall, you can't, when you make a polymeric reaction, exactly the same conditions will not make you the identical like polymeric all the time, like a polymer material all the time. So this is a little bit of problem here. Already this this spherical, and now when this reaction starts to happen, you can't really be sure that all the particles are identical, and like from batch to batch that they would be identical. So that's a problem. And that's why it's not very popular. So this is like this vertical. It is possible to have like this horizontal polymerization. And if you can, it's more difficult to produce, and there aren't, when we talk about polymeric phases for these particles, this is a little bit more like a theory side. There aren't that, oftentimes what also happens when we talk about some of the columns and column packing materials, we don't know how they are really made, because it's like a trade secret also when somebody makes a good. So it's not necessarily published all the either. So that's and there are certain things available, but not. But either way, if we could make, and somebody would make such materials, it is very stable. And you see here, because in this case, we don't have any of these lone groups here, these OH that would have problem with these basic compounds. And also it's more like resistant to like this, either to this low pH where we could have like this basically interactions, or at high pH that doesn't dissolve because it's like protected a little bit by this polymeric surface. But again, like you see, I don't really have any examples here. So I guess it's like nice in theory, but probably very hard to put into practice. But this is something you would see in the textbook and like from the theory. Yep.
I have heard that those are like a good alternative for like the thinking of the pH, but not for the pressure. You like it's I don't know. It's true that they are not very useful.
But now the thing is that, are you talking about well, it's just the polymeric surface. It's not the particle itself. It's not polymer. I think you might be talking about where the whole particle is a polymer particle.
Like previous classes say that these polymers are a good alternative from the silica column because they.
But this is still a silica column. This is not the polymeric column. You see, that's what I said. Okay. So this is just the surface is polymeric. It's not the particle itself. So that's the difference. We'll talk about this whole. Yeah. Then when the whole particle is made of polymer, we have like swelling problems and all kind of other things. Yeah, they are not as good. Yeah, so this is just surface. So we're still a silica particle, but how we are modifying this surface. So that's a little bit different here. Yeah, you can have where the whole particle is polymeric. We will get to that actually, and also some other options that are available. But yeah, and they have problems, definitely. So yes, this is just the surface. So like I mentioned, that one of the problems is that we have these free silanol groups left there that can cause problems for our basic compounds. And that's actually what is, you might have, I don't know if you have any experience, and there is like a procedure that we are doing, this end capping basically, is that we will have a like additional reaction to kind of like hide them or like remove their activity so that they wouldn't have these interactions. They wouldn't be ionic and wouldn't react, like wouldn't cause interactions with our basic compounds. So you can actually treat it with some other components. For example, this 3-methylchlorosilan. And basically what happens is that you would have these residual groups, and you would just basically just like put like a small, not like a long anything, but first you will do your like basic modification of the surface. So you had your C18s, and then you will do like a secondary reaction to just react, like hide away these residual groups that it would. So then you make your phase much more stable, that it and you will get nicer peaks. And you, in most, this is something, of course, when you buy a column, they always state if it's end capped or not. I'm not sure if there's like that much of a price difference. Maybe there is, because I think whenever you're doing, I think when you are like LCMS, really like targeted analysis, and then you usually use an end capped column. So, but again, some of the things, there's always like a little bit like things are on a timeline. So there was a time when end capped, they were more expensive, and there's like new technology and you have to pay more. Like for this solid core, the same. But when the timeline goes like everybody's doing end capped, it kind of becomes the norm, and maybe somebody else is doing without it, but it's not really. Sometimes why you might think that why would we even have those not maybe very good columns out there, but there are so many different applications that can be used in LCMS. And the other thing that's very important for the practical is that if you are a routine laboratory, you want to have the same column. So maybe you developed your method 15 years ago and you're just maybe doing like some kind of 3 or 4 compounds in your work. You want to just use that. You want to keep that column. You don't want to change it. And sometimes it can also be related to regulations. For example, in Pharmacopoeia, I don't know if you've heard, so this is basically a set of methods that are designed for analyzing pharmaceuticals or testing our pharmaceuticals. And this method, like there are like hundreds and hundreds of methods. And for example, like over the road, you have this, what is the state agency for, like, you know, when somebody wants to sell some kind of wants to come to the market and try, like, so they're just like, oh, this is like this new aspirin tablet. How do we test that there's aspirin in it? Then they open the book. There is a method. It says what column to use, what diluents to use, and you just do it. And you're not like developing a new method yourself. And then, like in these cases, they can also have like these old columns because they have been developed a long time ago. And the same for the standard methods that you might be required to do according to like an old method. Then you use this column that's, you know that it's not the best one, but you actually don't need the best one. So that's maybe just a little bit of like a backstory. Like sometimes we all, when we learn, when we working maybe in research, we like want everything to be the best, like, you know, but there are things that like a little bit ancient that are in use for specific reasons. And this is just remember that because I'm a technical assessor there for their accreditation, and I know that this is actually one of the places where I've seen like this very archaic, like quite large, like particle size, like, you know, long columns, like no end capping, and they need those columns, so somebody has to sell them. But there you see here that this end capped provides, so this is like a nice comparison between, so this I think was from Agilent Materials, that where they like showed what is the advantage of this end capped C18 column in comparison to the like the old type column where the peak is. Of course, there's flow rate also. Well, this is actually a faster flow rate. But still the peak is, so it's because of this end cap. So this component will be influenced by these lone groups there. Now we go to the polymer phase, where the whole particle is a polymer based. I think in most places where we actually come into contact with when we talk about solid phase extraction, then a polymeric particle is very common because they do provide different options also. And you can do different substitutions there also. The main one still is this polystyrene divinylbenzene. So it is hydrophobic, and you can use it for the reversed phase chromatography without, you don't really even have to do anything. You just, it works as is. And so here it looks like that. So it either can be also like porous, but these can also be made in such a way that you have a solid core, and then only like on the surface you have this polymer phase. they are good for like small molecules, and so they work quite nicely. The good thing is that why I also think that like usually the first columns that came into in our testing center also were because Karin was doing a lot of pharmaceuticals where she needed very high pH, and that was the only option. Like I think she did like 10 and 11, and that's where the only option. And to my mind, they are more expensive. I think so. Not 100%, at least 10. I haven't checked the prices. So, but the problem is that they aren't as efficient. So the peak shapes are not as good. But, you know, at one point when you want to do like at certain pH, maybe that's not your main goal, is not to separate like million compounds and have like nice peaks, but you even like want to get a peak, and at like low pH, you even will maybe not even get like a peak, or it will be so broad. So it's kind of your only option. The problem is that there is swelling, like you mentioned, that they can actually not be, you have to be very careful if you can even do gradient with certain eluents, you might not even be doing. And maybe you can just do like isocratic. Probably there are also like changing and becoming more. And I think where this actually helps is that these microbelucers, so let's just go back. Like these ones actually make it more practical than it, because only then this you can have this solid core that's very stable, and only then this very like a thinner layer of this polymeric material. So you have these like swelling and things are not as problematic, and if you do a gradient, it will like stabilize back faster, as opposed to when the whole particle would like swell up and have problems. So this is actually there can be some and also with these polymeric phases is that with these silica particles, they also need to have like some kind of a interaction with the wall also, that they wouldn't like you can't like damage this material inside, and also for this when these polymers are not very rigid either, so they can like start to move around, or you can like push them too much together, so like different pressures can have like a very big influence. You have to be very careful. So there are some issues with that, but the pH is an advantage. So this is what we are working with these polymer phases. Now we'll talk a little bit about how you can modify these silica phases. Like I already mentioned, this monomeric surface, which basically is the same. So you have the C18 or C8, or maybe even longer. I can't say that I've seen too many of these longer ones, but this is like the most common modifications that you can do. And it works well for, your non-polar analytes. So it's a very traditional way to modify it. So now this is the end capped version. So here we just only are putting this alkyl chain, but here we have also this. Now we are like, I have this doing what is like masking. We are masking basically this this lone group here. So, and you can see that this end capping reagent can also be different. So again, it comes down to whatever the process is, how they're doing. but or like what they have decided, but you can, and some other breaching groups, just like to make sure that whatever is on the surface of your particle, that this wouldn't influence your chromatographic separation. You only want this alkyl chain to play a role, that this is where the interactions happen with your analyte. So you kind of want to get rid of all the nasty things or like these impurities that are usually also present on the surface. And this will also reduce this breaching will reduce this hydrogen bonding also, because otherwise you will have these groups that can possibly also cause some hydrogen bonding with your analytes. So you kind of just removing everything else that you can only focus in this alkyl chain. So these are like the simple. However, you can do more. You maybe just not only that, but you can actually, because, you know, probably what Quite has told you, like when we have just this C18, obviously we are very limited on what the interaction with our analyte is. It's just this C18 and your analyte. But when we add something more, we can add, in a way, like this lone group had like interactions that we didn't want, but maybe there are some interactions that we actually would like in addition to what the C18 has. So we can add like this polar group here. So it can be different, but this will actually improve the separation of the basic analytes, because basics are like basic compounds can be problematic for the C18, and also polar components can be an issue. You know, also for reversed phase chromatography, polar analytes are what happens in reversed phase chromatography with the polar analytes. Yeah, exactly. So ideally, if they are like, we would like something that actually would maybe have like a little bit of retention, you know, so that it wouldn't completely. So that's why we can add this polar group here, that it would provide like this interaction there, that we have a little, like it's a little bit more, it's more selective than just like the C18, and you can play around with that, and it can be maybe like either like if it's like towards like phenols or acids, or like depending on what this polar group is, and then just the spacer is there just to that this polar group wouldn't be too close to the silica. But here it can be whatever, you know, like the column synthesis people have thought it's like a good idea. But yeah, so this is actually why you might want to add something. And I think this polar embedded, I'm not sure if this word is used for all of or like them, but this is actually quite popular if you know that some of your analytes are like have more like polar properties also, or you know that they are eluting just too early. What is the problem when analytes elute too early? What is usually why it's not very good? That you might not get a separation because they are like very similar. And what's the other thing that can happen is usually what sometimes happens. What? Column overload can happen. Yeah, if like too many is like coming at the same time. And also what happens, some like impurities also like what come early on in the column also. And also what about well, you haven't actually studied that, but also ionization is better when we have more organic phase, you know, in MS. You will start to learn. So when we increase the retention, it usually also means that once they reach the MS, the diluent composition is higher in organic than water, and then it usually is a better ionization in the MS phase. So that also like adds to that. in addition to all these like chromatographic separation things that we would like. So this is one of the why it's actually, I think, is marketed and I think is used from that point of view. And also you can have like phenol rings. Of course, this is definitely now more towards like polar aromatics when we have phenol rings here. So again, very targeted, and these targeted columns are quite popular because they're, like I said, the applications, there are so many applications, and even though the main one is C18, and just to keep it simple, but sometimes when you are doing very specific analysis, you really want the very specific conditions and very specific, and then it might be that you actually want something that, you know, is more targeted towards your polar aromatics, and then you would use this kind of modified, and there are like more and more and more this kind of modifications. And here I just found like a good, maybe like an example here is, so this is the double end capped. It means that this it's this to hide these lone groups that we can like do different ways to just end cap to make sure that like none of them is left. Then it's like basically not end capped at all. And then there is like this a bonded phase. So I think this was, so this is like this phenol one and like end capped also. And then this is just the phenol one, and not end capped. And then and this phenol one with what they say is just like some kind of bonded phase. Again, we don't know all the details how exactly they really look like what they're not saying. They're just like marketing in a way. But you see that they're all like phenol groups, like this phenol, the last part is like phenol, but whatever is happening like here can be different, and they all, even though the conditions are the same, you see that the selectivity is quite different. So even though they are all phenol, it doesn't mean that they are the same. So all these end caps are not end capped, or some kind of a bonded phase with end capping, whatever it exactly means. They provide different separation, and that's what makes life for chromatographist like very hard. And I think this also kind of shows why I think that usually when we talk about like doing like method development or have different courses about, and the first thing is like, first use the column that you have and then like go from there, because it's really hard to, and I think this is also why still the C18 is the most common one, when it kind of like, it works for most of the things. And if you get like a semi-decent results, you are, you know, you might end up trying 20 other columns and nothing might really change. So so that's why I actually like this kind of an example. There are a lot of application notes for like these column producers, and they usually have some kind of examples, and they show for certain analytes, certain matrices. So this is a good way to kind of get an idea that what might work for you, or even is it even like worthwhile to do it. So but yeah, these here like this are like more similar, but yeah, I don't know what happens here. Some compounds are still not so it's not only enough just that it is phenol and then it like solves all your problems for your phenol for your aromatic compounds. And then it's also possible to have a cyanophase, which is can also be suitable for certain applications that and the good thing about this is that this can actually can be used for the normal phase also. So it can depending on what kind of elements you have, it can work both ways. So that's and that's very with like when you have high polarity mobile phase. So depending on what phase you have. So, but this is also like very specific, like maybe for like amino compounds and not like just like any what you have. These are some of the options that you can do. And here is so they have different polarities, and then we not, in addition to what we are, this is like the easy picture, like the basic picture that, and then we can add all like these end cappings or some other groups, or then and play around, or like some spacers in between, and play around with this. And that's why there are a lot of different columns. And that's why we don't also know exactly, because different producers are probably doing things differently and trying to say like our column now, like this new one, it's like the best for these polar compounds, and like and have like a fancy name to it that doesn't really tell you anything, and you just kind of try. There are certain companies and producers who offer such a service that I think we with Quite have done it once. We were searching for, I think for seleno amino acids or something we did. And it's possible to send your mixture of your analytes, and they will test it on the column, and they will send you the results. So like, you know, all these producers are like their testing laboratories, and you're not sure, like, I don't want to purchase a column if I don't know it works. And they can like run it on the different columns, and they will send you the chromatograms, and you can basically decide that maybe this is something that would be actually a better column for you than like a regular C18. That was many, many years ago. I don't know if it's that, but I remember one case. And I remember, because that was the same thing, it might have been for Helic column actually, that they were advertising like, we have like this, all the best column, it's like new, and like now it like separates everything. And I remember that we were like, do we buy it? Like, but maybe it doesn't work. And then I remember that we like sent in, they analyzed, and then and we said that didn't really work. So that's, I have to be careful there. And yeah, like all the new things are like coming, like I said, here is like unique polar arc bonus reverse phase bonded phase. You see, there's like they are like just like pushing and trying new things, and you know, it's like the next or like novel bidentality C18 C18 bonding for extend C18 bonded phase. So like all kind of like this. No, it's so you have to be careful not to, because that some of these things are like can be market related. But you see here also what they are, which kind of makes sense, is that because they have that when we go back a little bit, what we talked about this when we have like this polymer on the surface of the silica, we actually can get like a better stability for higher pH, that it's more stable that you can use. And this is what they are saying, that because you are like bonding, you have this these silicas like in connection to each other and the C18, so it actually has a better pH. And I think this one, they are saying that it's this novel bonding reduces interactions between basic compounds and the silica, and improving peak shape. So basically everything that all these columns are saying is like best ever. So you have to be careful there. But they're trying to, I think this is it's a little bit funny, as if you have been working on the field for a long time. But when you're new to the field, you feel like, oh, like this column is solving like all of my problems, but probably not. So it's just, you know, as a word of warning, sometimes the best column is already in your drawer. So yes, the longer chains, the C18, and I think the other reason why the C18 columns also are very common, because they are very stable in a way that you can really run like thousands of samples and nothing happened. They're quite stable to higher pressures, and we want higher pressures because we get nicer efficiency, nicer peak shapes, better separation with higher pressure, and these all other columns can suffer from that. So that's why it still has all the advantages, even though maybe it's not the best from their like other like regular, when we think about just the interaction point of view, that other columns and faces might have like better interactions with the analyte and you get better separation. But if you can use higher pressure, faster flow rates, this can actually be more advantage than having a column that has like a very fancy spacer somewhere in between. So it kind of evens out. But they say that, oh, don't use like too high concentrations. Oh, this eluent is not very good. Then you are again like limited some other direction. So it's so that's the other thing. And I do think that we have seen, I think once, I think Karin has killed a this silica column with high pH. So it does happen. So it's not like a tale that don't use high pH. It really does. But I would say the low pH and like high water content are maybe less of a worry. Of course, like, and like I said, but then again, low pH values are usually not where in most applications that we are going for, but high pHs. And so you, when the column says that in this, that they come with this booklet and it says that don't use higher than 8, then don't. And if you're using higher temperature, then anyway, like then you have like a double effect. If you use high pH and like high temperature, you will lose your column. So always try to be on the safe range with these columns and also the same goes for the temperature. If it is allowed 40, it's always better to use like 25, 30 and not really go to 40 because it will in the end damage the column. And the same goes for different buffers, concentration of the buffers. If they are very aggressive, then they can also start to damage the column. So this is something to think about, not only pH itself. There are a few columns that I'm just mentioning. Is this like graphitic carbon columns? And why? So basically this is just a regular, this is basically, it's just like carbon. And it's very stable. It's not like your everyday column because they are very short. They don't tolerate high pressure or anything like that, but they are selective like towards isomers. So there are like specific applications where you can use such a column. And I've seen it in like articles, and that is usually the reason that you wouldn't use it like for regular application, because we know that we can't separate isomers with our regular column. So this is where it can be, but they are very like fragile and generally you don't get nice peaks. But for the isomer, this is an option. And also the problem is they are actually very expensive either. So you see all these problems and you would still think why it's in the market, but because there's like this very niche like area where it is used. Maybe when you are producing or like synthesizing different analytes and isomers, and you want to separate the isomers so that you can use them, or like so for these kind of applications, that's the only one. Or you want to detect them, or you may be doing some kind of like medical, I don't know, research where you want to know more about isotopes. So then isomers, so then it can be useful. So, and then I just want like like you see, like we could call, like we can talk and talk, and there's so many there, and probably every year there's more and more. But one thing I do want to mention is this monolithic stationary phases. This is something that I remember, like maybe 15 years ago, was like a big. It was thought that this is going to replace all the columns, like all these particle columns. So you see here, so when we talk about regular, like this particle column, so this is, have this little balls, but monolithic column is basically like one piece of a column. Like it's made of one piece, but the structure, how it is like made, is just like a coral or something, it's like in one piece. And what it does is that because of how the liquid is going, like how your element is going through, and it's one body, it can do a very fast separation, and like very specific. Of course, it's more like for larger molecules initially, also because how you can synthesize it, that you can't do it like for very small. But I do think that there are applications, and it depends on exactly how it's made. But the main issue was that you can actually get ideally you should get a very good separation with this, because how it's built, and it looks like, it's very stable, and it was something that was the reason that in our study group, we had one guy who was like doing that for his PhD thesis, and because it takes, how it works is that it's like they are short, fast, but separate good. So this was like the idea, and because it moves, like because of the diffusion, so it makes it like slower, so you can the separation is better. But they are very hard to make, and they are very hard to make it exactly the same way each time. You can imagine, like, because it's again like in a way how they're prepared, it's not like straightforward. But I heard, I think last time, and then I checked that Georg also said that they are coming back, and I guess probably the technology is advancing, so they have newer technology how to prepare these monolithic columns, and they are emerging back for also for like smaller molecules, and so maybe like for specific, but they are more expensive to make and more tricky to make. But I just remember that this is like with every new thing that everybody thinks that now, like this is the next thing, and we can throw away all our C18 columns. We're not gonna need that. But and I think the idea was also that you can use high organic solvent concentration, meaning that you don't have to like work when we talk about mass spectrometry, we ideally want more organic components so that it will vaporize better, so that you can get better ionization. So they were like specifically thought that like for MS it's like a good thing, but like I heard they are coming back and like more. So it could be something that we'll see if it's like sometimes it happens that science is going a little bit faster in that it's good on paper, but to make it like into practice, it's just technology is not there yet. I mean, isn't the same like with these electric cars that, it was many tens and tens years ago when it's not like a new thing, electric car, like it's a very, very, very old thing, but it just the people were not ready. The infrastructure was not ready. So it's the same here. There are some articles on Moodle if you want to know more. From the exam point of view, you are not expected to know all of these like details. It's more of to give you an idea what's out there, just to understand that they can be modified differently and why would we want to modify them like anyway. And I think this is like a little bit what my lectures are more. It's like Ivo and Koit, and they are academics, and I'm like more like on the practical side. And so don't worry too much if you don't understand exactly how some kind of separation. The most important ones we will talk about when we talk about the examples anyway, like when we like what column suits for, and so the C18 is suitable for and why. Then we can, so that you have some examples at hand. But overall, and like I said, it's actually on paper, it's hard to predict what analytes or combination and analytes works with what column. So in a sense, like there are so many variables, the pH, the element composition, you analyte, the concentration of the buffer, like what is the organic phase. So there are so many parameters to play, and then to add this column chemistry there also, there are certain rules, and I think this is about what this course is also, and it is to, I can say from the practical experience, it makes you think. And when you are working with an LCMS and doing method development, you need to think, and you need to consider different things and understand that it is a little bit trial and error. I've seen, like I said, I've developed a lot of methods in my life, and sometimes it seems that it should be easy and it's not. And in some other cases, you are like, that was easy, but somebody else hadn't, and you don't know why some other people struggled with that. And I have had both ways, and you don't know, and that's why it's very hard to replicate sometimes the articles also, that something is not mentioned. You don't know all the parameters, like even things like I've in advising one laboratory with their method development, and it matters, like if you take a column, like you are doing method development and you have a column that has been used for something else before, and you don't even like, oh, just I have this old column, I'll try, and you get very nice peaks, and then let's say it clogs up and you need to buy a new column, and you buy exactly the same column, and then it doesn't get nice peaks anymore, because something that somebody did before with this column caused it like some kind of like this modification in the phase. Maybe they did something like oily or something, and it just caused you to get nice peaks. And then I've seen these cases, and that's why it is so hard to really, give you the recipe, because there is no, the main recipe is to be very attentive and know that when these happen, that they are not anomalies, but there is some kind of a explanation, but you just might not never figure it out. Like I've said, I've seen a lot of things in my sleep, and so I know you just don't want to know like how many, and I can say, because it's a routine laboratory, and these things happen in routine laboratories, not only research laboratories. So one morning it just doesn't work anymore. You don't know why. But some things when you are choosing columns, like I said, some things that are good to know is that prefer shorter columns, because you get faster. You can use higher flow rates, And nowadays, really, you will save eluent and you will get faster. And the main thing is to get faster so that you can run more samples like on a certain time. Separation, yes, with the short-term column can decrease, but in most cases, if you have put at least some effort into get your peak separated, then these short columns with the higher volume, like if you use higher flow rate, you will still get very nice peaks. So, the pressure, yes, can be a problem also with them, but if you use higher flow rates, but overall, because they're shorter, you can use higher flow rates, so you don't have to worry. And the retention times are faster. So it is overall always start with the shorter column than the longer one. And the same for the particles, I would say usually don't necessarily go for the smallest particles. I think, like a 5 or 3, usually like stick to like not like the smallest ones, because the smallest ones you might have more clogging issues if you have like I think that's like, especially if you have like, I think now even these particles are so small that even if you are running like clean samples, and then you need, when you have these very small particles, it means that you need to filter your samples with like a smaller filter. These are more expensive. So in the end, you might not really win anything with these very small particles. So somewhere 3 or 5, I think, are, and again, this is the same, that maybe 3 were more problematic 3 years ago, like 5 or 10 years ago, but now they are getting better. But like never like take the latest, like the best. It's just like somewhere there. I think these are very, and again, you also always think also that what is your goal? Like if you don't have too many components in them, you don't need to get, because definitely the larger particle you have less problems with the pressure, clogging, and all of that. So it's actually better. The diameter, I think usually the diameter it's not something really you can choose. Usually you have a particle and the length, and there are not like very many options in that range. You will still, like when we think about HPLC and UPLC, I don't think, you just choose by the particle and the length. And but if you can, of course, then you will choose. But I'm just trying to think from what the columns I have used. The diameter is kind of like default, like a specific combination of the particle and length. So it might be something that you start to think when you're doing more like preparative chromatography, then you might think more about the diameter. But for analytical, then it's, but if there are, of course, if there is a choice, then again, you think that smaller one, you save eluent, you might have more issues with the back pressure, but overall it should be okay. But I think if you want like nicer peaks, then always like more like a smaller diameter is better when we talk about analytical separation. And like I said, no ideal, there is no ideal. I hope I would know by now if there were one, and I would just say, I would say that the ideal column is really like a good C18 column that, is doing the job. And this is like a good place to start. Shorter so that you can get the results faster. Because when I started chromatography, we didn't have like UHPLC. Now we talk about like 5 minutes, 10 minutes. My first was like 60 minutes, 70 minutes, was like around. And now if you think about, you're doing your bachelor thesis, and like the difference of me doing 60-minute runs and now they're doing like 5 or 10 minutes run, think how much more you can do during your bachelor thesis when I was. So, and to be honest, my bachelor one, I didn't even have an automatic injector. I did it manually. See, things change. These were the times. So many nights in the chemistry building. It's funny to think. But now everything is better. It's like faster and automatic. So you really can leave the building at 4, and in the morning you will have all the data when I didn't. so it's quite different. But yeah, so this is the basics of the columns, just to kind of give you a feeling, at least, or when you talk about method development, that you kind of have a little bit of understanding that you can modify them and you can but I would say overall, when you look at the literature also, you will see that it's quite standardized. You will not see very exclusive columns when you are looking for, I would even say, the articles that are related to method development. Somebody's doing, you will quite rarely see these fancy or very specific, because this is usually with the regular column you will get what you want, and always keep in mind what your detector is. And if you have a mass spectrometric detector, you should worry less about what your chromatographic separation is. Of course you want, but it doesn't have to be ideal. And another thing to just take a final note is that I would say the good column is that is robust, that it provides you the same results all the time. You know that you can run a lot of samples. You don't have to worry about it. And when something happens to it and you buy a new one, it works exactly the same way. I would say and I think this is why you see a lot of the same producers, Agilent, Phenomenex, some Waters, and usually these are it, even though there are a lot of other ones. And this is you stick to what you know. So on Monday, we'll do online, and then the Monday lecture will be very very practical about instrument. And again, it seems like my bad fortunes, and you can learn from them, and what to keep in mind when working with an instrument. So quite practical. And then on Wednesday, you will have Goit again, but on Monday, then we'll do online. Okay, and that's it for today.